This is a boring bar. It's used to enlarge hole diameters. And this is my longest cutting tool. As you can see, its length is about 70 millimeters. But with such an extension, the overall rigidity of the system is greatly reduced. So today, I need to make a device about 150 millimeters long, and despite its length, it must remain as rigid as possible. On proper lathes, such tools are mounted directly into the tool holder, but my lathe is very flimsy, and that would reduce its rigidity even more, so I decided to take a different approach. I need to prepare the material for the blanks. I took a rod, it's steel 45, 25 millimeters in diameter, and a block made from some basic steel, 40 millimeters thick. I don't have a bandsaw yet, so I'll have to use a cutoff wheel. At the same time, I'll check how much the wheel's diameter shrinks after cutting such a thick block. So right now, it measures 79.5 millimeters. Even though it's a big piece of metal, it got so hot during cutting that touching it with a bare hand is painful. And indeed, the temperature turned out to be almost 100 degrees Celsius. I measured the wheel diameter again, and it turned out that only 1 millimeter of the disc was worn away. That's a very good result. Now I just need to remove the burrs and rust. Then the blanks will look decent and will be ready for further work. While you're watching, I'll quickly tell you about this block. I need to make a rectangular block. Although it looks more or less rectangular, it's actually not. All the corners are slightly off. In this project, I want to train myself in true precision. That means for measurements, I'll use a dial indicator instead of a square, as I used to do. I'll sweep each surface and then machine it. Only this way can you achieve really high precision. As you can see, I first leveled one surface, and then based on it, made the other surfaces either parallel or perpendicular. Basically, it's a very simple task and matches the level of a first-year machining student. And honestly, this whole project is quite simple, and a skilled craftsman would complete it in one work shift. Overall, the part came out very geometrically correct and high quality, but there's an annoying issue. On one side there was a taper. I decided there was no point in milling off 3 millimeters from the entire surface just to remove it. I'll mill it off separately later. Here's where the part will be installed. And in its rectangular shape, the part looks way too bulky, so now I'll cut these edges at 45 degrees. The shape is ready. Although the part still looks a bit rough, but that's fine. First we'll handle the geometry, and later I'll work on the aesthetics. Now I need to mark where the hole will be for the clamping screw from the original tool holder. First, I measured the screw body diameter, it's exactly 11 millimeters. Then I measured the distance from the edges to the screw and added 5.5 millimeters. That gave me the distance to the center. When marking, I still made it an even 33.4 millimeters. It might seem like all I need to do is drill a single hole, and that high precision isn't even necessary here. However, I want to do everything as correctly as possible. If I missed any important step, please correct me. This is a standard 5mm drill bit. It's generally considered that the maximum drilling depth should not exceed 5 times the bit diameter. In my case, that's 25mm, but the blank is 40mm thick. For situations like this, there are special long drill bits. A tight fit isn't required here, so I didn't bother with countersinking or reaming. Even so, the result turned out great, and most importantly, the part's edges line up perfectly with the edges of the compound slide. Now comes the most critical and difficult step. I need to drill a hole 25mm in diameter and 70mm deep. This will be my first time working with such dimensions. I'm very nervous and will try to do everything properly, following correct drilling techniques. To ensure accuracy, I started with a very thin center drill. Stop. Right now, I just wanted to close my eyes and rewind time 5 seconds to pull that damn drill out of the blank. Did you see what happened? The tip broke off. Damn it! What should I do? I can't drill a new hole elsewhere, I have to somehow remove the broken drill tip. I'll try using a carbide-tipped drill bit for glass. Unfortunately, it didn't work. The tile/glass bit has a pretty wide web, and while it might scratch tile or glass, it can't grab a piece of broken high-speed steel drill bit. I'll have to bring out the heavy artillery. I had bought a special 4.5mm tungsten carbide drill bit just for emergencies, ordered it from AliExpress for about €5. It's brand new, and now it has to work. Slowly, little by little, 1/100 of a millimeter at a time, I managed to drill out the broken piece. But to make progress, I had to apply a lot of force to the carriage handwheel. I kept expecting the drill to catch and snap. Luckily it didn't happen, but later, upon closer inspection, I saw that the cutting edge got slightly dull. After that, it was simple. First, I used a long 6mm drill to make a through hole, and then gradually increased the drill bit diameter. For you, it was just a few seconds, but I spent about 40 minutes drilling. Inside, the hole is full of deep grooves. I'm still not much of a driller. Although probably, if you want a smooth hole, you need to bore it with a cutter at the final stage and then finish it with a reamer, then it will be perfectly smooth. I decided to try inserting the shaft. The drill bit was 25mm, so the hole must be slightly bigger. And the shaft is calibrated, it's exactly 25.000mm. However, it wouldn't go in. No way. Then I remembered what they told us back in 8th grade during a special lesson when a doctor explained how everything works. Lubrication is necessary. Yes, the first time it's always hard to insert, but thanks to the oil and by rotating side to side, it eventually worked out perfectly. Now I faced a problem I couldn't solve myself. The shaft's diameter is 25 mm, but my lathe spindle bore is only 20 mm. This means I couldn't machine the ends. So I went to a friend who has a proper lathe, and he did everything for me. Big thanks to him. Normally, boring bar holders and adapters are made so that the tool is clamped with screws. But I'm not clamping a tool, I'm clamping a cylindrical shaft made of much softer steel than a cutting tool. Over time, the screws would deform it so badly that I wouldn't be able to insert or remove the shaft. So I need a different solution. Now, the final stage, installing the clamping screws. I'll use 2 screws with strength class 12.9, which guarantees that the hex socket in the screw head will stay sharp and won't strip. These holes are not as simple as they seem. I prepared 6 tools: a center drill, a through-hole drill, a tapping drill, a clearance drill, a tap, and a countersink for the screw head. Everything's good, except the handle of the clamping screw points toward the lathe chuck. That's bad because it would interfere and hit larger workpieces. I need it to point toward the operator when tightened. It needs to turn about 3/4 of a turn. To achieve that, I have to reduce the height of the part. I measured the height difference between the fully tightened and the rotated position, exactly 1 mm. Here, I made a common mistake. Out of laziness, I installed the milling cutter directly into the drill chuck and started milling. Of course, there's no rigidity, and the metal was just scratching, not cutting. Then I installed a proper collet chuck, and everything started working correctly. I got a little carried away, maybe now the handle will turn too much. Let's check. No, it's perfect. Exactly how I wanted it. Technically, the part is now fully finished. However, it looks very rough. I thought about painting it, but a lathe constantly produces sharp chips, and the paint would peel off quickly. So I decided to polish it with different abrasives. It's far from perfect, but I did my best. Now I need to make this extension piece. It's a double-sided holder for cylindrical boring bars. One side will hold a 6 mm shank, and the other a 10 mm shank. This means I have to drill 2 holes exactly opposite each other again. Unfortunately, I had long drill bits, both 6mm and 10mm. When I installed it in the lathe and aligned it visually along the compound slide, it turned out to be precise enough, no extra adjustment needed. The drilling process itself had some nuances. At first, I tried drilling just by manually turning the handwheel, but the drill moved very hesitantly. Then I switched on the automatic feed, and it went much better. When I heard the motor start to strain, I immediately retracted the drill and cleared the chips. I first drilled from both sides with the 6mm bit, and then enlarged one side with the 10mm bit. As a result, I got a good, precise bore, a proper holder for boring bars. The boring bars themselves are secured to the shaft with set screws. It's very important that these screws don't stick out beyond the shaft's outer contour, otherwise, the shaft won't fit into the holder. That's why I used very small 8mm set screws. Although technically, set screws are a little different, but here they are just clamping screws. I had a broken R18 drill bit, and I had kept the shank. So I made a scriber from it to scratch a line exactly in the center of the shaft. This line is perfectly perpendicular to the clamping face for the boring bar. It's needed for fine-tuning the angle of the cutter. Even though the shaft was calibrated and rust-free, I still polished it with an abrasive wheel to match the tone of the clamp it will be installed into. The most satisfying stage, assembling everything together. I can't believe I made it myself. Maybe you'll laugh at my words. After all, there wasn't anything very complicated here. But I really enjoyed designing and building this tool. Now it's time for testing. There could be two issues. First, there might not be enough rigidity, the cutter could chatter, bounce, and fail to cut. And second, I'm not completely sure whether the cutter center must align exactly with the spindle axis. I read in a book once that it should be slightly lower. For testing, I took a small aluminum tube with an inner diameter just over 8mm. Before, I wouldn't even have tried to bore something so small. Let's see if the tool is rigid enough, if the cutter even fits into such a narrow hole, and if it actually cuts. Honestly, I'm thrilled. I really didn't expect it to work this well. And the boring bar was extended by about 100mm during the test. I originally made this tool for a much more difficult project. I'll need to bore 16mm diameter at a depth of about 120mm. But there, I'll flip the holder and use the stiffer 10mm boring bar. Well, no spoilers, you'll see everything next week. It turns out that I made a deep boring holder, but it ended up being very versatile. I can even use it for small bores too. Before, I clamped cylindrical boring bars directly into the tool holder, stacking a bunch of plates underneath, and of course, it was hard to keep the height right, and the cutting quality was poor. But this new tool is really awesome. Maybe we even earned your heroic like. I'd really love to hear your opinion about the tool I built today. What flaws do you see, and what could be improved?